Let's talk about some very common sequences. This is our objective for this class. It's going to be, in particular, we're going to talk about the unit sample. We've talked about that before in EE431. The unit step, sinusoid, how to go back and forth between sequences and the unit sample, the complex exponential, and then we'll talk about sampling. We mentioned it briefly so far. We're going to take a little closer look at it. We're going to talk about the definition, the fact that in discrete time, there's a limited frequency range, which is just bizarre. And then we'll talk about the sampling theorem, which is completely non-obvious and really surprising. Common sequences. Let's talk about the unit sample. The unit sample is radically changed from what we worked with in continuous time. You'll remember in continuous, when you integrate a unit sample, what was the area underneath the unit sample?
1.
1. And so when you integrate the unit sample from 0 to t, what do you get? Do you remember?
An impulse.
No, that is an impulse. The unit sample is an impulse. Now you're going to integrate that unit sample, that impulse, which has underneath its impulse an area of 1, and what do you get? Let me just remind you of that. So in continuous time, we had this thing called the unit sample, also called the unit impulse. We drew it like this, and we said it had unit area under its whole thing. What would we get if we integrated it? Gordon, I'm going to ask you, if we integrated it from negative infinity up to here, what's the area underneath that unit impulse?
It's 0.
Yeah. And then what if we move our point of integration from negative infinity up to just before 0, what would we get? What we're doing here again is we're integrating from negative infinity to t of our top function. Mathematicians have trouble with our reusing symbols, so we use a dummy symbol. We want to find out what is our integral of this between negative infinity and this point here. So what's the area underneath this, Gordon?
0.
Okay. And then what happens just as we pass this 0 point? What's our area from negative infinity to 0 plus?
It's 1.
Right. And then as we continue on, it's the same. So my question is, Gordon, why don't you finish up? What's the integral of an impulse in continuous time?
It's the unit step.
It's the unit step. All right. So we're going to do the same game with the unit sample in discrete time, except it becomes so much easier because we already know what the unit step looks like. It looks like this. So now what would our unit sample have to look like so that when we integrate it, we get this? What do you think, Alex?
Well, going off of what it used to be in continuous time, it makes me think that the sample at 0 would have to be like infinite.
Now let's see what would happen if it was. We'll just draw the arrow going up to infinity and every place else is 0. In continuous time, when we talk about areas, now we're just going to have to talk, and we talk about integrals. In discrete time, we're going to have to talk about sums. So if you sum up these values, does this have a sum of 1? No. What would it have to be in order to have a area of 1, just like in continuous time?
Just going to be a value of 1.
It's just going to be a value of 1. That is so much more intuitive, isn't it? Now it's just simply 1. It's defined everywhere. Of course, discrete time doesn't really have areas, but if you think about the area of that is 0, the area of that is 0, the area of that is 0, the area of that is 1. And so in discrete time, it just makes so much more sense. This unit sample, you don't have to define it under an integral. It's just simply a unit sample. So it's equal to 1 when n equals 0, and it's equal to 0 otherwise. Some schools actually teach discrete before continuous, but by the time you get to the end of this lesson, I think you'll recognize why most schools do not teach it in that order. So as just as an example, what is the unit sample impulse Noah evaluated at -6?
0.
Yeah. What is Noah, still you? What does this thing look like?
It would just be the unit step shifted over.
That's it, except it's the unit sample stepped over.
Or yeah,
That's right.
unit.
That's right. Just like that. So if it's a sequence of n, it looks like this, and this is unit sample time advanced by 1. Okay, so we've already talked about what the unit step is. You can draw it as something like this. We could just as well define it too. It's equal to 0 for n less than 0. It's equal to 1 for n greater than or equal to 0. All of a sudden, we have to worry about what happens at 0, and we didn't need to worry about definitions like that for our in continuous time because there was no energy. And now n equals 0 has a definite associated energy. And just like in continuous time, the integral of a impulse is a step. In discrete time, instead of saying the integral, we would say the sum from k of minus infinity to n of our impulse of k is equal to u of n. And just compare that with the continuous time. Although we don't usually write it, the variable of integration, that's what it would look like if we said from tau, from negative infinity to t of the sample, d tau is equal to u of t. So this is discrete time, this is continuous time. Same idea, we're just replacing integrals with summation. Let's talk about sinusoids. Actually, there's almost nothing to talk about sinusoids. In discrete time, we'll say x of n equals a cosine omega naught n plus phi. So Mitra tends to use a different symbol for phase. This is just a different symbol. It means the same thing, the phase angle. And this is our frequency, but it's our discrete frequency, which turns out to be subtly different than the continuous time. Because we talk about continuous time frequencies a lot, I'm going to show you the symbol. We use different symbols for discrete frequencies than continuous time frequencies. So this is our continuous time frequency. And this is just a capital omega. So it looks like the symbol for resistance units, but this is lowercase Greek omega. This is uppercase Greek omega. And we'll be talking about the difference between discrete frequency and continuous time frequency shortly. One thing I want you to realize, so this again is discrete time. This is continuous time down here. One thing I want you to realize is that in continuous time, is it possible to have a omega naught that's equal to 0? Is that something, or is that mathematically not allowed?
I don't see why not, sir.
Sure. It wouldn't be very interesting. It's not changing, but that's allowed. What's the highest continuous time frequency that you can have that's unique? Fawaz, what do you think? What's the highest continuous time frequency that you can have?
Would it be infinity, sir?
Exactly. And they're all different. Whereas in discrete time, it varies between exactly 0 and it can go up to and include pi. And at least that's the unique range of frequencies. If you plug in a value higher than pi, it will be equivalent to some other discrete frequency map between the range of 0 to pi. That's not clear yet. It will be when we get into sampling at the end of this class.